Okay, here's a wave equation example. So suppose you have a string vibrating with fixed endpoints, and let's just say that the length of this string is about 4, and the equation for string equation is UTT is some c squared times uxx, right? So I'll just do the simplest. I'll just say UTT is uxx. So in this case, c squared is set to 1. So that's the simplest one. Now, the endpoints are fixed, so they don't change. Therefore, u of 0t and u of 4t should be 0. That means it's a fixed endpoint. Okay, and then what we are going to do is initially we will pull this string, okay, and then we're going to release it. Right? So initially we will have ux of 0 look like the following. I'll make it as 4 minus absolute value of x. Let's see, 5.2. No, sorry, x minus 2 minus x minus 7. Sorry, that should be okay. So if you do that, then the graph looks like the following. Initially, it's like that, okay? And you're releasing it, so it will start going back and forth. Okay? And then your ut x00 is set to 0. See, because it's a second order differential equation in terms of t, not only your initial condition should be provided, your first derivative should be provided in the initial condition. Okay? Just like in the second order, you had to give y of 0 and y prime of 0. The same story here. Okay? So, and because we're pulling it and then releasing it, our initial velocity is all 0 because you're releasing it. And then we want to see how this thing is solved. Okay, so let's try to solve this one. So again, you apply the separation of variables. What does the separation of variables say? It says you want to set uxt as a function of x and the function of t, plug it in, apply the endpoint value, endpoint condition, and the equation itself, and hope for the best. That was our original approach, right? So you plug in the left side. What do you get if you do that? On the left side, what do you get? T double prime. I'll just write x times t double prime. On the right side, what do you get? Yeah. So x double prime t. Okay, and then if you divide everything by x and t, you get t double prime over t equals to x double prime over x. And it's the same story. Once you have a function of t on the left side and a function of x on the right side, it has to be a constant. Instead equal to negative lambda, and this is also the same story. Your endpoint becomes a condition on x only. X of 0 and x of 4 should equal to 0. Because if you set t of t equal to 0, it gives you a trivial solution. And this one, along with this condition, gives you what x could be and what lambda could be. X should be, because you have the endpoint 0, what kind of function that gives you that? 0 and 0. What function is this? Sine. Graph of the sine is like that, right? So at the endpoints is 0 and 0. Okay? So sine is 0. The solutions will become sine of n pi x over 4. Of course, there's some constant times this, but we ignore the constant because we're going to multiply the constant later anyways. And then lambda is the second derivative. That's our lambda. And then now you put it back in here, and we get the following. It's t double prime equals to negative lambda t, which is negative n squared pi squared over 16t. And if you move this to the other side, we have the following equation: t double prime plus n squared pi squared over 16, t equal to 0. And this is a second order, so it actually requires a characteristic equation r squared plus n squared pi squared over 16. And it actually gives you what? Gives you equal to 0, gives you two imaginary solution, r equals to n pi over 4I. So that gives you t either equal to sine c1 sine n pi over 4t, or c2 sine c2 cosine n pi over 4t. All right. Now, if you so both of them are valid. You actually need a one constant here, another constant there. And if you put them back together, you have ux of t equal to some constant times, let's write down an instead of c1, an sine n pi over 4. Let me write cosine first, because that's the custom. So cosine, I'm going to write cosine first, plus bn sine n pi over 4. Oh, these are t's right by my x's. T times the function of x, which is sine of n pi over 4x. This one is x. So that's a function of t times function of x. And because this is true, this is a solution to both these two, from n equals 1 through infinity, I can just add them up from n equals to 1 through infinity. So that's the general solution. Okay. And then when you plug in 0 for t, ux0 is sigma of n equals to 1 through infinity of an sine n pi over 4x. Right? So that means since ux0 is 2 minus x minus 2, I need all the sine series, Fourier sine series of this thing on the right. That's what you need. On the other hand, this condition here, right? This condition means you have to differentiate this once, and then you plug in 0. That will actually make this part 0, because cosine differentiates to sine. When you plug in 0, that goes away. And when you differentiate sine, you get n pi over 4 times cosine. So you get n pi over 4 times bn times sine n pi over 4x to be utx of 0, and then you say equal to 0, you get bn equal to 0. Okay? So bn will equal to 0. So since I know what bn is, I know that bn is equal to 0, all I have left is finding ans. So we have to do the Fourier sine series of this, but this calculation won't be that easy, so I'll leave this other parts to you. Okay, so once you find the an, you put it back here with bn being 0 and an whatever the Fourier sine series is. That gives you the answer for this wave equation. That's how it's done.